Now we have the microphone to thank Emily and her team for organizing this wonderful workshop. So thank you very much. I'm honored to give this talk. However, it's was hard to prepare this talk because, as you may have known already or seen already, in the next two sessions, a lot of my PhD students and students will give their talks, and I will not spoil their results. So I decided to focus on instrumentation and give you some concepts, and the results are then up to my team and their presentations. We came up with a lot of contributions to this conference, and we're working on reconstruction, instrumentation, and particle science. And as you see, the green box is the largest. So we are very interested actually in instrumentation, but this will not work without reconstruction and particle science, of course. Instrumentation, I mean hardware. To produce hardware is a lot of hard work. So you have to have an idea of what you would like to design. So when you have an idea of measure the particle distribution, you have to design a magnetic field, and you have to simulate this before you start to produce a coil for producing the actual field. And you have to have an idea of the complete concept of a scanner, and there are a lot of boxes with details, and each of the boxes is a challenging task. We have to have a lot of new ideas in manufacturing science, which you see here. For example, some supporting devices to hold the coil material at the positions where it should be to have precise fields. And also you have to have ideas of cooling concepts, because I mean there's a lot of power dissipated in such coils. Okay, so I focus here on three lines of instrumentation in our laboratory. This is magnetic particle spectroscopy, an asymmetric coil topology, so a single-sided scanner, and a scanner based on the field-free line. So we started in 2008 with the first concept. And spectroscopy is, of course, about learning something about the particle core. The magnetic remagnetization should be measured, and so we look here at the magnetic curve. So we have heard a lot of talks about this, and we have already seen this idea of sinusoidal excitation, the mapping of the sinusoidal excitation to the magnetization, which is distorted. It is picked up within a pickup coil where we have the derivative of the magnetic signal, and then we transfer this to the spectral regime in Lübeck, where we find the fingerprint of the magnetic particle. And this is something we started with designing the signal chain, and you see here in blue the transmitted, and in green the received chain. And here, of course, you need signal generation, a lot of amplifications, band passes, where you produce a very harmonic sinusoidal excitation, because you would not like to have already in your transmit paths harmonic waves that cover then your reaction of the nanoparticles. So then you have the nanoparticles, and measure in the receive coil the small signal from the particles, leading this to a bandstop filter, filtering out the fundamental frequency, and doing ultra low noise amplification before you record the signal. So this is the concept that we started with in 2008. You see here just the inductive, and this is together as a resonance here with the capacitor bank. And here inside you will find, if you look in the reception coil, of course, and here with some advanced supporting material, we built into this shielding box, where this actually was the first signal generator in MPS and all labs in that year. However, as we all know, this concept suffers from the signal from the excitation. So The band scope is okay, but a cancellation technique is needed, and so the second generation MPS is already with cancellation. You see we have some advances in producing of coils, which looks much sophisticated, and together with a capacitor bank here. And what you see here is when you look in the shielding box, that we have two devices, mirror devices, which produces the same signal, transmit signal. However, we have here the device for the probe, and here this is the device where we measure just the air signal, and we just couple the air signal then against the signal from the measurement device to actively then cancel out the fundamental frequency. Okay, this is the signal that we have measured. We have seen 80 harmonics when we excite with 25 kilohertz. And what we also then did is based on the Langevin theory that we solve the inverse problem. I mean, when we have the theory and we have the measurement, then we can fit the parameters and receive a distribution of particle sizes. So our spectrometers then give as an output this distribution of the particle core sizes. Okay, so since then a lot of steps have been done and milestones fulfilled to come to a sophisticated signal chain design. For example, here is tunable inductive, which can be tuned when the inductive is already built in the machine. So when you have the feeling that your matching is not good enough anymore, then you have the possibility to mechanically tune the inductives to make a fine tuning of the matching of your filter channels. Also, sweeping frequency spectrometers are very interesting because we would like to see the reaction of the particles in different bands. And what we see here is in spectrometer also again with cancellation techniques. You see here two identical devices, so mirror devices, and one of these measured just the air signal, and here with a geometrical possibility to fine-tune the cancellation in different frequency bands. And where we are today. Today, we already know, and we have heard this in many of the contributions at this conference, that sometimes we measure a signal in a zero-dimensional spectrometer, which looks fine, but the particle will not work on the MPI device. So, and this means that the particle reacts differently on different situations in the scanner, obviously, and we found out, and others did already, that the particle react different on different trajectories. So here you see some fundamental trajectories that we produce in a new kind of spectrometer. Here you see this new kind of device that we built in our laboratory, and there is a poster outside of Matthias Gräser with some details of this. Where you can measure some fundamental trajectories, for example, a spiral, Richelieu, and a radial trajectory. And color-coded, you find here that the translational magnetization direction is in blue, and the rotational magnetization direction is coded in red. And what you see is then that for the spiral, for example, where we have almost a rotational change of the magnetization, the rotation speed is so fast that the particle cannot follow the speed in terms of Brownian rotation, and this damps the signal. So the signal here is rather the signal decay is much faster than, for example, in this radial excitation. And the Richelieu that a lot of us are using for our scanners is a mixed case of both. And it is very complicated where the particle is and what the particle sees then as type of reaction to the excitation. So, but this can be studied with our new kind of spectrometry, and there we are today at this line of instrumentation. Okay. Then to imagers. The first image I would like to introduce is the asymmetric coil topology. Here, a design of 2009, published in 2009 by Timo Sattel, one of our alumni. What is the idea behind? I mean, when you have this conventional design of having here in the vertical direction the combined selection field and drive field coils, and here in the horizontal direction another pair of drive field coils, then even today we have a problem of the confinement in between the coils. So the measurement field is very small. We have only preclinical scanners today. So our idea was to get rid of this confinement in the sense that when we shrink this lower coil, for example, and we shrink this so that it fits concentrically into the upper coil, does this produce a field-free point? Yes, it will. And more precisely, it will produce two field-free points. So this is then our arrangement that we built in our laboratory. This is the first 2009 published realization of these such coils. And here you see again this realization together with this filter bank, and here some racks. This is only a one-dimensional device, and so we have some free places here in our racks for the other dimensions as well. So how does it come that this kind of topology produces a field-free point? So let's have a look at the two coils. So the inner coil is with current in the left direction, and the outer coil here in blue is streamed with current in the right direction. And let's see how the field strengths behave on the axis of the coil. So for example, at the yellow point here. So the field strength for the red coil starts here with a very high value. Because the coils are very near to this point, it starts with a high value. But then when you go away from the device, then we have a very rapid decay of this field strength. Okay, so for the blue one is already far away from the axis, and so the starting field is not as high as for the red coil. However, due to the geometry, the decay is not as fast as the decay for the red one. So we have somewhere in space a crossing point of these field strengths, which the modulus of these field strengths is the same, but the coils are streamed in opposite ways by the current, which means this is the cancel-out point for the field strengths. Below and before and after this point, we have field strengths. And when we now modulate, for example, the current in the inner coil, then we are able to push and pull the field-free point away and against this device. Okay, so this is one-dimensional excitation, and we did some experiments with two dot functions which we push away from the device, and you see how we can resolve then these two dot functions. Okay, so this is our first device, and cooling is one of the critical things we can report, and Tobias Knopp, I think, can report what happens when you forget to switch on the cooling fan, because then one of these coils here is transferred to licorice wheels. And so cooling concept is something which in the second generation of single-sided scanners is one of our critical issues. You see the oil cooling connections and the housing where the coils are swimming in oil. How from 1D to more dimensional imaging for single-sided concepts. So I've explained that in the conventional geometry we have this adding of orthogonal pairs of driving coils, and so we have a natural way to find, for example, a Lissajous trajectory. But how to do this in a single-sided way? And the answer is exactly in the same way. We need orthogonal fields to push then the field-free point from the axis in the lateral direction. And you can do this in different manners with a second coil pair. And We have studied a lot of geometric situation of this and come up with a double D-shaped situation where we find out that the field free point can be steered and then almost with a UV. Yeah, here's a simulation of what we have now constructed and how this can be seen then in front of such a device. And here, one of our first results, you see here a 2-dot phantom, and this is above this device. You see here the receive coils, and here the 2 points which are imaged, and what you already see is that the point which is far away from the device has not such a good definition, which comes from the degradation of the field strength when you go away with the field free point from the device. Okay, so what is our application for this? Our dream is to find a miniaturization where you can hold this as a handheld scanner like an ultrasound device. The idea is then, for example, analyze the axilla and in the sentinel lymph node biopsy. What is this? The sentinel lymph node biopsy is done today with technetium, a radioactive tracer, to find the lymph nodes which must be analyzed when there's a tumor diagnosed in patients, in a breast tumor, for example. So the metastatization of a tumor runs over dissemination of cancer cells via the lymph path. And in earlier times, when there's a cancer, there had been a total resection of all lymph nodes to analyze this in a histology department. However, this is a very reduced quality of life after this, after having no lymph nodes in the axilla. So the idea is only to resect those lymph nodes which are actually connected to the tumor via the lymph path. And this is the sentinel lymph nodes. And you can measure this today with technetium, which is administered in the tumor or beneath the tumor, and then you find in the scintigraphy here the tumor and here the sentinels, which you have to need to get out and bring it to the histology department. The anachronistic thing about this, however, is that today the clinician uses a Geiger-Müller counter to find then the sentinel lymph nodes. And we think that this can be augmented with SPIOS and with our single-sided device, which then can be used in future for real-time 3D guided surgical intervention. Okay, there we are. This is the situation today, and in between, some time ago, we also started from this expertise the idea that when we have this flat coil set, we may integrate this coil set into a patient table, so that the patient table is then in the catheter lab and reduces there the X-ray by using SPIOS instead of iodine and these X-rays. Actually, this image, this videos have been shown this morning by Nico, and we have seen that the cardiovascular application is something which may work for magnetic particle imaging. And what we then first tried is a huge coil that will be integrated into the patient table. You see 2 of the technicians here, which are very crucial for this project as well. However, what we learned then, we have a lot of sensors in this kind of sandwich-like coils that we have to produce for temperature censoring, and also the field quality is single-sided in the end, which is has a restriction in penetration, as I said before. And so we need huge coils to have acceptable field of view. And from this point, we thought, okay, when we have huge points, then the coils must be too large to fit on the patient table. Maybe this is a concept where we may introduce arena-like or elliptical coils into the patient table in the catheter lab. And we studied this as well. We have some of these devices here and measured the field quality that will be produced by such devices, and however came up with very low quality of images that can be expected. So then we thought maybe we can use supporting coils above the patient. So not the complete set of single-sided arrangement, but a supporting coil, single coil above the patient in 2010. And then in the next step we said, okay, what about two single-sided coil sets where the field free point is matching each other, so that we have a kind of handshaking between the two field free points. And this reduces the current that you need for variation of the field free point in space very, very much. So this is something which we studied in a lot of design studies for the images that we can expect. However, we stopped this project at this point because to this time Philips came up with the idea that 25 kilohertz is too dangerous in terms of PNS, and we have to scale up the frequencies. And then we thought, okay, what to do? We would not like to change actually to 150 kilohertz. We would like to stay with our competency in this regime, because all our filter banks are optimized with 25 kilohertz. How can we receive then with a lower gradient and lower fields the same quality with field-free line? And so we came up with field-free line, which may produce the same quality with lower PNS. Okay, but this is a decision in 2012, and already in 2010 we had the first demonstrator for the field-free line, so we had some competencies already. So what is this about? It's about SNR. So when we have the field-free point, then of course the gradient steers the resolution which we can expect. However, the higher the gradient, the less particles are in direct flipping than when the field-free point goes over the particle. And so the strengths will be reduced. So therefore, one may really think, and this is, I think, the same idea in the Berkeley group, that when we excite a complete line of particles, then the signal-to-noise ratio will raise. Okay, what do we need to do this in not in a mechanical way, but in an electrical way? So we need a generation, a rotation, and a translation of such a line in space. And actually, unfortunately, also here, Philips was one of the pioneers who said, okay, this is in principle possible. Yeah, you can produce and rotate and translate a field-free line. However, you need some 32 coils to produce and rotate a coil. And the authors then say this is impossible to produce because it's 1,000 times the power loss of a field-free point. But then, fortunately, I had an excellent PhD student, which is Tobias Knopp, to this time, and he proves that actually 3 coil pairs are enough to produce a field-free line, and 4 coil pairs produce an optimal field-free line. And he could show that power is then reduced to only 1.4 of the field-free point, and this is the point where we said, okay, then we can realize this. And actually, what we did is we did this first demonstrator in the publication of 2010. And however, what we have to have in mind then is that artifacts may arise from imperfections of the field-free line. Because, I mean, the field-free line isn't the field-free line in infinite lengths. So what we have to live with is with inhomogeneities and nonlinearities, and this produces artifacts, as we know this from CT, for example. So, and the first step, therefore, was to think of optimization of coils to reduce these inhomogeneities and nonlinearities. And for example, you can think of circular coils, rectangular coils, which are planar or curved. And here a study has been done by Marlon Erbe for the deviation of the field-free line from a certain coil set compared to a perfect mathematical field-free line. So, and what you see here is that you have the curved circular coils. Then the next is the circular coils planar, and the red one is the rectangular coils planar. And what we've found out is that the rectangular coils in a curved way have the least or best the performance in terms of field deviation and also reduce power loss. This is then the first measurement of such a coil set, and this is the first realization. And based on this, Klaas Bente and Matthias Weber produced the idea of having such a device. This is a cut of such a device, and this is a realization. Okay, and this is now able to rotate and translate and produce a field-free line. So here you see the complete setup of this machine, and for example here some of the sophisticated receive coils that we produce. And what we have now here first in simulation is the situation as we know it from CT. We have a field-free line running over the set of distribution of nanoparticles, and we always receive the sum of all magnetization changes. And this produces a sinogram. And from the sinogram, by the filter back projection, you can then receive the image, the distribution of the nanoparticles. Here is the second generation of this dynamic FFL imaging machine. So, first results, an L phantom of 2 millimeters in the thickness, 12 millimeters on the long side, 8 millimeters in the small side. Here you see comparison to 1 cent. And this is our first result then, very disappointing actually. And what we learned from this result is two things. The first is we need deconvolution. I think also Berkeley uses deconvolution. You named this differently, I think. And we need two steps of deconvolution. The first is that you have this relaxation. The relaxation is that when the field-free line goes over the particles and then come back, the particles remember that they have been polarized in this direction, and this is not the state in equilibrium. And so we are not ready with relaxation, and we have to cope with this, and we have to reduce the errors from this by deconvolution. Yeah? So this is without, and this is with exponential deconvolution of the relaxation. And then, of course, the point spread function from the Langevin function can be used to make a second deconvolution, and this is then the result of the L. This is the phantom over this, and to compare this maybe to the situation of the vessel tree of the brain. We have, for example, the L line here. This is the L we have measured in the dimension that you can compare with the vessel tree of the brain. Okay, this is the complete concept, and you see this poster of Klaas Bente and Matthias Weber and co-workers outside of having this device and having this concept of reconstruction. And what we actually can do is a real-time imaging. What you see here is Klaas Bente, who pushed out a phantom, pushed out a phantom in real time, and this is the phantom. And I will not spoil now the result of Matthias Weber's talk, and he will give his talk in a few minutes, so be patient. However, what I would like to show you is here an online reconstruction of this phantom. We have a phantom with 2 dots here, and this phantom is held here in the middle of the measurement field and then turned. And what you see then in real time is the sinogram. And you see from the phase shift of the sinogram that this is real time. Yeah, so real-time imaging with a field-free line. Third generation field-free line means scaling up. And scaling up here is a rapid-sized scanner of 17.3 centimeters. And also here we have a lot of things to care for, extremely to do with the heat up of the coils. We have some 1,000 amperes and 4,000 kilowatts on this coil set, not in phase always, of course. However, we have to care for the heating of the coils, and this is the result in our laboratory at the moment, and we are very eager to have the first result in a few months. What we also then think of is scaling up this to human size and human size image scanner. And Gael will give this talk in a few minutes, so I will not spoil his results. But however, this in principle seems possible. However, so my feeling is somewhere we're landing somewhere here, which looks slightly. You know what this is? So this is a detector, one detector of the Large Hadron Collider in Geneva. So here we are. So here we are today with our last line. Where are we tomorrow? And tomorrow we hopefully receive the Bruker machine this year. And our task will be to build an insert for thermotherapy, so that we can combine the imaging with the therapy. So this is not only done then hopefully by the magnetic fields, but also will also integrate an ultrasound device, a small ultrasound device to make high through inside the machine. And this is the project name, Smart Application of Magnetic-Based Particle Therapy and Imaging, SAMBAPT. Thank you very much. Questions? Questions?
Bir sürüler.
Oh, everything here. That's wonderful.
Thank you very much.